Welcome everybody. This is Dr. Daniel Barth back with you again on the How Do You Know program. And this is episode 93. In the news this week, I think we all know what's in the astronomy news this week. It's the eclipse. I thought about putting a Bill Clinton-esque headline up on my show notes. It's the eclipse, stupid, but I thought, nah, I love my audience and I'm not going to do that. In any case, I certainly hope y'all had a great eclipse. I had a lovely time. I had a tremendously enjoyable eclipse. And this eclipse was seen perhaps by more people than any other in history. And not just digitally and online for people who followed it from around the world. I'm talking up close and personal. This totality was seen by people in the Mexican states of Sinaloa, Durango, Coahuila, and then in the United States in Texas, Oklahoma, Arkansas, Missouri, Illinois, Kentucky, Indiana, Ohio, Pennsylvania, New York, Vermont, New Hampshire, and Maine. What a spectacular event. Now, here in the state of Arkansas, where the Explore Studios are located, we're in a small state. We have about 3 million people. And the state government indicated that we had some 1 million to 1.5 million visitors to Arkansas on Eclipse Day. Probably on the higher end of that, because we were one of the few places with nice, clear skies. Now, when you take a state of 3 million and you say, ooh, let's increase your state population by 1/3. Well, guess what? Infrastructure takes a beating and traffic can be awful. I knew this going in, so being clever, I chose to go see my total eclipse adventure in the lovely hamlet of Ponca, Arkansas. Now, if you're saying to yourself, where the heck is Ponca? Well, that was kind of the point. Ponca has, let me count them for you. Ponca has 9 permanent residents. There are 9 people who live in Ponca full-time. On the eclipse day, there were hundreds and hundreds there. We went to a lovely place called Steel Creek Campground along the Buffalo River. You drive... What's that, sir?
It's a great place.
It is a great place. You drive down into a gulch, and you drive down several hundred feet down into this gulch. You emerge on a level plain, and you've got this lovely meadow in front of you. The Buffalo River is on the far side of it, and then sandstone bluffs, 100 to 150 feet high, rise up from the opposite side of the river. It's just a place of great beauty, and for observing, because you're literally down in a gulch. The night skies are spectacular, but it was a great place to view the total eclipse. We got there about an hour early, and we set up. I have a pair of 127 millimeter aperture binoculars. That means a binocular with a 5-inch lens for each eye. And these monsters are almost a meter long, 36 inches, and they weigh over 12 kilos, so it takes a very beefy tripod to set them up. And we had to take 2 cars. My wife and myself and my brother and his wife came along, and we needed 1 car for the binoculars. The SUV was filled up with the binocular equipment, and then the other car had things like chairs and a cooler and other stuff like that. Well, we get to the campground. As soon as you start to unpack a pair of giant binoculars that are 3 feet long, that's a party in a box, folks. I've often said that a telescope is a party in a box, but man, the big binoculars draw a crowd. And as soon as we got them set up, we had many people wandering over. And of course, everybody asks the same question. They see you looking through there. Is that real? And then quickly followed by, can I try? And as a wise fellow said, when you go out to do astronomy, any event like an eclipse, you can document it, you can observe it, or you can share it. Pick one. I picked share. I had my binoculars up, and yes, I was looking. My brother and our wives were looking, but we were giving turns to other people. Most of the time we spent, my brother and I, telling people about the eclipse and the giant binoculars and sharing the experience. What was really nice, we had folks from all over the world. We had kids and adults of every age, and I was trying to document the eclipse a little bit. So I was taking my cell phone and I was putting it in front of the binocular and taking some snapshots. Now, if you've tried to take a cell phone photo through a telescope, and make no mistake, these twin binoculars are a twin telescope, you find that positioning your cell phone takes a lot of practice. It's difficult. Well, people were seeing me go up and I was just going, ooh, eclipse, and getting photos and people came up, can I try? Oh, sure. Well, after a while, they're like, I can't get it. They were wobbling around their cell phone. So I ended up spending an awful lot of time at the eclipse saying, give me your phone, click, there you go. How did you do that? Lots and lots of practice. But we were able to see sunspots. We were able to see the full progression from first contact exactly on time at 12:34 at our location. And we were able to watch it go through totality. Now, because we went to Ponca, we were just inside totality. We had about 30 seconds of totality. We could have gone farther into the path of totality, but that would have been hopping on a major freeway. And one of the nicest things about Ponca, it's at least a half-hour ride from any major highway. It is really, it's out in the middle of the Ozarks. And
no service at all.
No services, no indeed. You can go about 20 minutes to Jasper and you can find restaurants and a gas station.
Yeah.
But in Ponca itself, you're on your own, kids. And I had just such a lovely time. And there's a picture. I'm hoping producer Paul is able to put it up for you. There's a woman here wearing a cap and she has her phone. She just has the biggest smile on her face. This woman was from Germany. And her English was accented and a little bit broken, but we understood each other perfectly. And I said, can I take a picture of you? She said, oh yeah, gut. And she had her phone up and she tried several times. And then she got the picture and she turned and looked at me and she was holding her phone. She just has the biggest smile on her face. To me, this was one of my favorite eclipse pictures. Not because it was a brilliant photo of the sun or capturing that prominence during totality or Bailey's beads. None of that. This, for me, was about helping other people enjoy a celestial wonder. Feeling the sky get darker, the temperature falling, the stars and planets coming out. We saw several planets. We were able to see stars. The birds stopped singing. The insects the crickets and whatnot started chirping, and it's like when totality hit in Steel Creek Park, everybody, a huge cheer went up. Horns were honking in cars. It was like being in Times Square for New Year's Eve. It was the most spectacular experience. And my little brother, who had never seen such a thing, he's not an astronomer like yours truly, but he wanted to come down. He was so jazzed up. So I hope you all got to take family with you. I hope you got to go out and see the eclipse and have fun. If you have photos that you think are particularly good, not just of the eclipse, but of you and your friends and family sharing that eclipse, if you'd like to send them to me at Astronomy for Educators, that's FOR, astronomyforeducators@gmail.com. And if it's okay with you to publish them, I would very much like to share them with my friends at Explore Scientific, perhaps get them up on our website, and put a selection from viewers of my program up on my social media. So if you're interested in sharing one of your pictures, and like I said, my very favorite ones are not of the sun. My very favorite ones are of people enjoying this cosmic event. And I had
So
some.
Scott was in Texas.
Ah, okay. Yes, Scott Roberts. Yes, our friend and sponsor. Yes.
So he says we were lucky to get clear skies
Yes.
because in Texas they had to look at it through thinning clouds.
Yes. We had an almost cloudless sky. There was a few high, wispy cirrus clouds. But as I said, unlike most locations, Arkansas had nice clear skies. A lot of other places, I've heard from other people, friends and people who trade here at Explore, and many of them said, my eclipse experience wasn't very good. We were clouded out. But here in Arkansas, we had the prime experience, and I hope you did too. So there we go. Let's move on to today's main topic. When I picked this and said, I'm going to do a show about dust, I told my wife and I told my brother, my next show is going to be about dust. And they looked at me like, why are you doing a show about dust? And my brother just he ran his hand along some furniture in my house and goes, there you go. I go, well, some of that's from outer space. He's like, no, it's not. Well, sure it is. And when we want to talk about dust, it's one of the most insignificant things, and yet it has such a crucial role in our universe. So I want to tell you all about dust. Anytime you want to talk about dust, you have to go back to a German astronomer named Heinrich Olbers. And I'm sure I'm maybe not saying that quite right. Apologies to any descendants of Herr Olbers. But basically, this begins with something called Olbers' paradox. And he wasn't the very first one to come up with this idea. Actually, Johannes Kepler of planetary motion fame, he was the first. But it was Olbers who popularized this idea more than a century later. Olbers, also a great astronomer, he discovered the asteroids Pallas and Vesta, and he did a lot of early work on orbits of comets. So, very accomplished gentleman. And he's also the one who proposed that the asteroid belt was made up of pieces of either an unformed or a destroyed planet. And people were divided on that idea. But what Olbers is talking about with Olbers' paradox is he's discussing the idea, is the universe infinite? And if you've gotten beyond pretty elementary math, you've probably struggled in math class with the idea of infinity, something so big it's uncountable. At the time, in Olbers' time, in around 1800, there was much discussion. Is the universe finite or infinite? Well, Olbers said it cannot be infinite. And his argument was theoretical, but it makes a lot of sense. Olbers said, let's start and consider that the universe is indeed infinite. It extends forever in both time and space. Well, Olbers said, if you were in a forest and the forest was infinite in all directions, you couldn't possibly see out of it no matter how clear the air was. That's because wherever you stood, every line of sight would eventually hit a tree. And Olbers argued this idea is the same. If you're looking out into space, and space is indeed infinite, then if you consider space like a series of nested shells, each shell, if it's the same density, has to contain more stars. It's like saying, okay, if I paint successively bigger barns, there's more surface area. I'm going to have more paint. For the universe to stay the same density, each shell would have to have the same average number of stars per cubic parsec. And so each shell would have more and more stars as you consider the universe like a series of shells. This is if you're not familiar with this idea, it's an idea from calculus. Don't sweat over it. But if you do the math, although each successive shell is bigger, and although the distance to the shell is greater, there would be more stars there, and so each shell would be equally bright. So if you took spherical slices of the universe, each sphere, think of like a jawbreaker when you were kids, the different layers of candy. Well, each shell of the universe would be equally bright because each shell would be farther away but contain more stars. And so Olbers said, if the universe is infinite, and remember, he's thinking of space as completely empty, and he had good reason to do so. He said if the universe is infinite and each line of sight would have to land on a star, then the sky at night should be as bright as the surface of the sun. Because no matter where you look, you're staring at a sun. And you think about that and your mind starts to boggle a little bit. But wait, if I'm looking farther out and I'm constantly seeing, our experience on Earth isn't like this. If you took a walk, say, in a downtown square, festooned with Christmas lights at holiday time, and you might say, oh, there are so many lights. Think about Times Square in New York on Christmas, right? Or maybe your own hometown. Well, if every line of sight ended in a light bulb, then the whole square, the whole area, everywhere you looked, would be as bright as the surface of a light bulb. Well, if we look at that on Earth and we say, well, that's not true, and you think about, oh, I take a look at a picture of a forest, that's not true. I can't see a tree no matter where I look because the air isn't completely transparent. There's dust, there's humidity, there's fog. Lots of things interfere with your vision. But Olbers said, no, no, no. Space is empty and therefore perfectly transparent. And so since the sky isn't as bright as the sun, the universe cannot be infinite in scope. And we look at this idea from Olbers, and when I've given this to astronomy students and said, why is Olbers wrong? And I would tell my classes, I can tell you right now, Olbers' paradox is not a paradox. Olbers was fundamentally wrong about something. What was it? Well, many students over the years came up with many ideas. Well, are the shells less dense as you move away? And all sorts of different ideas. Well, nobody ever comes up with space isn't transparent. You think about it. You look out in space and, well, it's empty. There's no air. You can't breathe. So how could it possibly not be transparent? And in our own solar system, our experience is that the Earth is quite perfectly transparent. Thank you very much. Except not always and not everywhere. If you've been fortunate enough to be out somewhere dark enough to see the Milky Way, or if you've taken a picture of it, you notice, oh, there are bright areas in the Milky Way and there are darker areas in the Milky Way. And if you do a little bit of exploring, people tell you, oh yeah, the dark areas, that doesn't mean there aren't any stars there. That means there's a cloud of dust blocking the light. One of the most famous dust clouds is called the coal sack. Well, gee, if it's called the coal sack, guess what? It's like this area in space of complete darkness and no starlight shines through it. Does that mean it's terribly dusty like grandma's attic? No. The amount of dust, you can talk about grains of dust in the singular digit numbers, grains of dust per cubic meter, and that's still a very dusty area of space. And if you're thinking, oh, only a few grains of dust and that's it in a cubic meter, well, that's almost nothing at all. And you would be completely right. The thing is, if you travel through almost nothing at all for a great distance, you're going to hit something. Well, beams of light shining through a dusty universe, if it's an area with more dust than usual, then in fact, the light hits that dust particle and it's absorbed and blocked. Well, you think about dust and you say, gee, is this everything? No. Modern cosmology has added to the dust idea from Olber's time, and we now know that there's a couple of reasons why we don't see light from distant stars. One of them is dust. The other one is Einstein and Hubble's friend, redshift. Because the universe is expanding, light from distant stars is redshifted. So indeed, even if it was a bright yellow star, if it's far enough away, the expansion of the universe redshifts the color of that light down from yellow into red, and eventually even into infrared. And as we know, the light from the Big Bang has been redshifted all the way down into the microwave region, 2.7 centimeter wavelength. So when we look at this, a great deal of light we now know is redshifted out of the visible spectrum, contributing to a dark sky at night, but the rest is actually blocked by dust. Well, it turns out the role of dust in our universe is more than just as a blocker. It's not just there to interfere with the free passage of photons. Dust doesn't just block light, it absorbs energy. And if we think about the difference between dust and gas, it's simply this. Gas is on the atomic or at most molecular scale. Gas molecules are small enough that they act like ideal particles. They fly around at greatly high speeds, they hit things and they bounce off in a perfectly elastic manner. Gas will expand to fill available space. Gas molecules don't like each other. They tend to expand to fill the space they're in. And they don't stick to surfaces. To get gas to stick to the surface of a planet, it's not any chemical or adhesive nature of the gas itself. It takes gravity to do that, which is why smaller bodies like Mars have less atmosphere than Earth, and even smaller bodies like our moon have no atmosphere at all. So when we say dust absorbs light, what's the difference between blocking and absorbing? Well, I could block something and have it bounce off and effectively be unaffected. If you shine a flashlight at a mirror, the light bounces off the mirror. The mirror, so far as we can measure, is not affected. Dust is different. Dust is different. If you hit a gas molecule with light, it will get more energetic, it'll get hotter, but then it'll cool off again. A dust particle is going to absorb that light and then re-emit it. Now, this is different from bouncing off. If you shine a light on a mirror, that light beam reflects, it bounces off. And so the color's unchanged, the wavelength is unchanged, the speed is unchanged. Just the direction is different. With a dust molecule, a dust particle, when the light hits, it's actually absorbed. It's like flicking a cup of sugar at a puddle. Okay, you might see a splash, but the sugar dissolves and it's absorbed in that water. When light hits a dust particle, it's absorbed. That light is gone. The dust particle now has more energy, and it will re-radiate as infrared energy, heat. We all experience this now that we're getting warmer weather. You go out, it's a nice sunny afternoon. You open your automobile, you step inside. Wow, it's hot. How can it be this hot? Well, because visible light shines through your car window. It strikes your dash, your seat, your steering wheel. It's absorbed, and then it's only re-emitted as heat. So we get in and grab our steering wheel on a nice July day. Wow, that's hot. I need a towel. I need a pair of gloves. I can't grab the wheel. We get in with shorts on and sit down on the seat. Ouch, that's too hot to sit on. That visible light coming through the window has struck the seating surface. It's been absorbed. It's made the seating surface hot. And now that energy can only go away in infrared light, which, as you know, takes more time. And surprise, guess what? The glass of your car doesn't transmit infrared. It blocks it, reflects it backward. So once the light comes into your car, heats up those seating surfaces, and that infrared energy can then not get out of your car very easily. The only way it can is to heat up the entirety of the interior of your car, and then your car essentially glows in infrared because it's hot. Well, we look at this and say, well, gee whiz, what does this have to do with the cosmos? It turns out a great deal. Because gas molecules do not stick to each other ever. They bounce off and ricochet. That's the whole gas being elastic, expanding to fill a container. If the gas molecules stuck together, it certainly would not do that. Dust particles do stick. Now, that means if you have material in gaseous or liquid form and it gets cold enough, it can condense and then solidify. So we see this process in a solar wind. Ionized particles are emitted from the star as a solar wind. They get farther away, they get cooler. Particles can stick together, form more complex molecules and dust particles. This idea of particles colliding and sticking is a process known as accretion. Accretion is the fundamental mechanism of planetary assembly. Now, this isn't necessarily the way stars assemble. Stars assemble from gas and some dust, but it's compressed and held together by gravity. Planets don't work that way. Planets, the dust given off by a star is compressed into a disk, so it looks like a ring, like around Saturn, and that compression forces more particles together. They stick, they collide. The bigger they get, the more often they collide with other things, the more often they collide and stick as opposed to collide and shatter. And as the particle's size gets larger, eventually you get planetesimals, you get something up to about 1,000 meters in diameter. Now gravity is significant and it starts pulling in more material. So this accretion condense property of planetary formation starts with dust. Also, we know that dust is essential in the formation of stars. And you might say, well, why? And there wasn't always dust. What happened before? Well, in the very early universe, what we call population 3 stars, these were stars with no dust in them. The universe was just hydrogen, helium, tiny little insignificant bits of lithium and beryllium, but it was essentially hydrogen, helium. No particles, no metals, as astrophysicists say. For these stars to form, it took enormous clouds of gas. The gravitational fields had to be tremendous. And these first stars, these population 3 stars, they would have been on the order of at least 70, 100, perhaps even as much as 1,000 solar masses, bigger than any stars seen today. As a result, they would have burned very hot and lived very short lives and died in a spectacularly violent supernova explosion. And the whole time, of course, stars synthesize elements. They're making things like carbon, oxygen, nitrogen, silicon, all sorts of wonderful things up through the periodic table, up through iron. These elements were able to form solids, the metals, and carbonaceous materials, and that's how we get dust from stars. Now, in a modern universe, today, dust is essential to the formation of stars. Again, why? It has to do with that ability to absorb light and then re-radiate it as heat. And again, we come down to a fundamental difference between dust and gas. If a star is purely gas, as that gas compresses, it gets hotter, and hot gas tends to expand. So you have this fight between gravitational compression and thermal expansion. And so if you have pure gas, it's very hard to form a star, you have to have an enormous mass of material to get enough compression to actually start a star. Why? Because as the core gets hot, it makes everything expand, and when it expands, it cools off. So the star, protostar, would tend to pulsate, and it wouldn't kick over into nuclear fusion in a true modern star. But when you have a little bit of dust, and it doesn't take much, just a small sprinkling, like you'd add salt to your eggs, just a little bit, these dust particles are constantly absorbing high energy light and then re-radiating it as heat. So essentially, this dusty material inside a forming star acts like a radiator. It takes heat from the core, which is preventing the core from being crushed and starting fusion, and it re-radiates that heat, which allows the star to maintain compression, and ultimately it tips past that crucial temperature and pressure threshold when nuclear fusion begins, and the star will start fusing hydrogen into helium and eventually run all the way up the cycle, if it's big enough, through iron. So the dust is crucial to star formation. Without dust, your star formation is slower, less efficient, and you cannot possibly make small stars like our sun, which are calm enough to be friendly to life in planet formation. These great big violent population stars, like blue giant stars today, are so big and they burn so hot and so fast, there's simply no time for planetary formation in their short, violent little lifetimes. So, this dust, apart from just stars, where does it come from? Well, this is where the interesting new stuff comes out. New research, just in the last year, indicates that type 1a supernovae are major producers of cosmic dust. And when we talk about a type 1a supernovae, what we're talking about is a binary star system where one star has died first and become a white dwarf. The other star continues to live its life cycle, and as the companion star becomes a red giant, it expands out, it loses its gravitational hold on its outermost layers, and this material starts infalling onto the white dwarf. Well, you can only pack material onto a hyperdense object so long until the compression and the gravitation sets off a thermonuclear explosion, and bang, there's your type 1a supernova. And we've had to start looking for other formations, mechanisms for dust, because there aren't enough giant stars in the universe to account for all the dust we see. And again, we look at galaxies like the Milky Way, like Andromeda, like Triangulum, and we go, wow, we can see the dust lanes. If you photographed Andromeda, and I suspect many of my listeners have, then you'll have seen the dust lanes. And of course, if you photograph the Milky Way, the same thing, you see the dust lanes. Well, these core collapse supernova from the very big stars, there's not enough of them to account for all the dust we see. And so this type 1a supernova is being looked at by astrophysicists and astronomers as being the source for the missing dust that we know is there, we just don't know where it's from. And we look at this process, the type 1a supernovae process, and this is a process that goes on all the time. And some type 1a supernovas are, they're periodic. You get a flash and a bang, and then things cool off for a while, and then the red giant starts dumping material again. And so sometimes you can have a sequence of 1a supernovae. The other thing, of course, type 1a supernovae, also known as a standard candle. Why? Well, white dwarfs are all very similar objects. They can't be too much bigger, or they'll collapse into a neutron star. They can't be too much smaller, or they would simply evaporate. They wouldn't have the gravitation. So white dwarfs are within a very small range of physical sizes. And because that's true, dumping this hydrogen plasma onto them, how much hydrogen plasma you have to dump before it goes bang is very well known. And because the amount of explosive in the bomb is very well known, surprise, the bomb, the thermonuclear explosion, the supernova, is very, very consistent. And again, type 1a supernova, important. Why? When one goes off, you know almost precisely how much energy was released and how much light was there. How bright was it? And if you look and say, ooh, how bright does it appear to me, and you know how bright it actually is, you can calculate the distance really well, which helped us as one of our distance ladder calculations that Hubble and others did that helped us determine the scale of the universe and how far away other galaxies were. So we look at these supernova explosions and say, okay, it goes bang. How does it exactly form dust? Well, it turns out these pairs, in order to function, if you're seeing a type 1 supernovae, that's a very old star system. It's old enough that one star has already gone through its entire life cycle and died and become a white dwarf. The other star is on its way to dying and has become a red giant. Well, red giants, one of the interesting things is that as the core burns hotter, because it's fusing helium now and not hydrogen, it causes that gas and plasma of the star to expand. When these outer shells of the star gets farther away, surprise, the gravitational pull of the star itself is much weaker. The star expands, and now it doesn't hold on to its outer shell nearly as well as it used to do. And because of the violence of the core burning helium, the amount of material the star is ejecting through the outer layers is now much greater than earlier in its life as a dwarf star. So this red giant is expelling a massive amount of solar wind. Again, this is radiation, ionized atomic nuclei, and individual atoms of things like carbon, nitrogen, oxygen, all these little nuclides that were synthesized in the core of the star over its 10 billion year lifetime. As these particles move away, they don't form dust right away, because if you have individual carbon atoms, they're going to act more like a gas than they are like dust. However, when the 1A supernova goes off, essentially it goes off in a cloud of these gaseous and individual molecular materials that have been ejected by the star over millions of years before this nova occurred. And when this shock wave radiates out through this essentially spherical cloud of gas, surprise, it's compressing this cloud from the inside out. We don't think of compression that way. If you wanted to demonstrate compression in a science class, you could blow up a balloon and then give it to a child and say, here, sit on this. And we could watch the child sit on the balloon. We could see the balloon squish a bit and go, there you go. You're compressing. Take the balloon and hug it. It takes force and pressure to force that balloon into a smaller volume. That's what compression is. And we usually think about pressure squeezing from the outside, squishing something into a smaller size. It's not working that way. We have an explosion at the center of this cloud, and the explosion, pressure wave, shock wave is moving out faster than the surrounding gas and material can get out of the way. As a result, this material is compressed with this shock wave going from the inside out. And this compression is what's forcing these carbon and nitrogen and oxygen atoms together, allowing them to form solids. Things like CO2 and NO2 and NH3. So you're getting things like ammonia, carbon dioxide, oxygen gas, just larger nuggets of carbon dust. So you're getting all of these atoms being forced together. Consider your high school chemistry class. If the teacher said, mix these two liquids and watch the reaction, guess what? The reaction isn't going to happen while the liquids are in their own separate little test tubes, is it? You've got to pour one into the other and bring these molecules into contact with each other before a chemical reaction occurs. Now consider this massive shell of expanding molecules. Well, if you're going to compress that stuff and form solid particles, and you're going to get a chemical reaction to form to make things like O2, CO2, CH4, HN, all sorts of things. If you're going to make these molecules, you have to get the atoms in proximity to each other. It's not like on the Earth where you have nice things like gravity field and atmospheric pressure. No. Out in space, we have none of that. It's this compression wave from the supernova, and the compression wave is coming out from the center and basically slamming into that ionized material that's moving too slowly to get away from the explosion. That material is being compressed. That's creating your chemical reactions, and that, in fact, is creating the dust particles. Now, these dust particles will spread out through the universe, and they will mix in the interstellar medium, and the next time you have a cloud of hydrogen helium gas which starts to compress, it's no longer pristine as it was in the early universe. Shortly after the Big Bang, when these clouds of hydrogen and helium were compressing, that's all there was. But run the clock forward a few billion years, when the next cloud of gas begins to compress, now that cloud isn't pure, it's dusty, it has a small percentage of contaminants, but that small percentage of contaminants, those dust particles, change everything. They allow the star to radiate away its excess heat as it forms. That allows smaller clouds of gas to compress. That allows smaller, more stable dwarf stars like the sun to form. And smaller, more stable stars like yellow dwarf stars like the sun, they live long enough. They're not like the early giants. Instead of living 10 million years, now they live 10 billion, 1,000 times longer. Instead of being extremely huge and violent, they're smaller and calmer. They don't give off the huge amounts of ultraviolet radiation which can destroy molecules and ultimately life. They're not too cold that they don't provide enough heat and UV to drive the processes of light. So it's really dust that made it possible for our star to form. And because it makes it possible for small stars to form, it also makes a calm place in the universe for planets to form. And after all, what's a planet? It's this lovely place for chemical reactions to happen. The Earth gives us this lovely surface upon which chemicals can land and meet and link. It gives gravitation to hold things in place so they don't drift off through space. And it also gives us a place where the planet rotates. We can collect a dose of solar radiation and then get out of it for a while. So we've got this nice rotation to give us alternating day-night cycles. All these things are made possible because dust. When Carl Sagan said, "Be noble, for you are made of stars, but be humble, for you are made of dust," he wasn't kidding. I am, you are, we all are. And as the old book says, ashes to ashes and dust to dust. From dust we come, from dust we will return. And the universe keeps on turning. That's all we have for you today on a very dusty topic. I hope you've enjoyed today's program. If you do have a chance, please pick up a copy of Star Mentor. Also, I happen to have heard the Star Mentor book will be available in a couple of weeks here at Explore Scientific. So it'll be available at our Amazon site as well as if you drop into the store or call us up. So we'll be stocking the Star Mentor book. And if you would like to get a... What's that? I will. If you'd like a signed copy, all you have to do is call up and order a copy and say, hey, would you have Doc sign that for me? And if you'd like to say, this is for Robert, happy birthday, or something like that, don't give me a book to write. But if you have a short message you'd like inscribed on your book, yes, I'd be happy to do that for you. And as always, I truly appreciate y'all tuning into the show. Next week, Monday, we will not be on. I'm going to be at the Northeast Astronomy Forum, or NEAF. That's in upstate New York. And if you're planning to come to NEAF, please come by the Explore Scientific booth and look for the old guy and say hello. Be thrilled to meet you. And I will be back the week after with our next How Do You Know program. Thank you all very much.